In this video, we will wrap up our discussion of Taylor series by investigating Taylor polynomials and their associated remainder estimates. So the idea is as follows. If we are given a function f of x, and many times in applications we have a function that arises, we typically do not need an entire Taylor series to do basic types of approximations. Instead, what we might want is just a certain degree Taylor polynomial. So we let t sub n represent the nth degree Taylor polynomial. And note this is defined above. The nth degree Taylor polynomial of a function is defined as being just the first terms in that Taylor series representation. It would be the first n plus 1 terms because you go up to the nth derivative term. And note that's not guaranteed to be exactly equal to your function, so there's always going to be some remainder part left over. And once we come up with this nth degree Taylor polynomial, much like in the past where we've had a sum of a series that we have estimated as the nth partial sum plus some associated error, we want to know how good of an approximation do we have. So the question is, what type of approximation can we use for that remainder? And the remainder can be estimated via Taylor's remainder formula. So if we have a function f of x which is expressed as its nth degree Taylor polynomial plus the associated remainder, then that remainder term is bounded above by this number big M over n plus 1 factorial x minus a to the n plus 1, and this is for some interval of interest which is given to you in the problem. Now a few notes here. The m is an upper bound on that next derivative, the n plus first derivative. So in some sense this remainder term looks an awful lot like just the next term in the Taylor series. The only thing that you're doing different is you're thinking, how big can I make this x minus a based upon your interval? And then additionally, how big can you make that next derivative? So let's look at a few common examples and see exactly how this formula is used. For the function e to the 2x, let's start off by finding the second degree Taylor polynomial centered at 0. And once we have that, we will estimate the accuracy of this approximation on the given interval. So t sub 2 of x, let me just write down its formula to get started. So t sub 2 of x centered at a equals 0. This will be the Taylor series terms up through the second power, so those first three terms. F of 0 plus f prime of 0 times x plus f double prime of 0 over 2 factorial times x squared. So for the Taylor polynomial of degree 2, we need to determine three numbers: f of 0, f prime of 0, f double prime of 0. So typically, finding this Taylor polynomial is going to be the easier part of the problem. So let's calculate a few derivatives. If f of x is e to the 2x, f prime of x is 2e to the 2x, and continuing on using the chain rule, f double prime is 4e to the 4x, and for future usage, let me note that f triple prime is 8e to the 4x. Furthermore, f of 0 is equal to 1, f prime of 0 is equal to 2, and f double prime of 0 is equal to 4. Substituting in those values above, we have that t sub 2 of x is f of 0 plus f prime of 0 times x plus f double prime of 0 over 2 factorial x squared. So that would be 1 plus 2x plus 2 x squared. Now that we have the Taylor polynomial, I would like for us to do two things. First, I would like us to estimate how good this approximates a function, that is, come up with an upper bound on the remainder, and then visualize this graphically to see exactly what is going on. So I've cut and pasted the information from the previous slide. What we would like to do now is estimate kind of an upper bound on that remainder term. And what we've seen in our formula is that this is less than or equal to big M over, and we go to the next number. So 3 factorial, x minus a, so here a is 0, so it's x, an absolute value, cubed. And two things here. We have an interval that we are working with, so minus 1/2 is less than or equal to x is less than or equal to 1/2. And we have that m is an upper bound to the third derivative, specifically on the given interval. So looking at our third derivative, the third derivative is 8e to the 2x, which is always positive, so we don't actually need the absolute values. But there would be nothing incorrect about including them. Furthermore, let me note that this function is increasing. That is, graphically, as you move to the right, it is getting bigger. So if you would like to know how big this function can be, you would plug in the largest possible value of x in the given interval. So that largest possible value of x in our interval is 1/2. We can plug that in for x. So this will be 8e to the 2 times 1/2. So just 8e. And note that coming up with this value of m is typically going to require us to make some type of observation based upon that derivative, in this case a third derivative, being increasing, decreasing, or just how big can we make it on the given interval. So once again, this 8e is going to play the role of m. So this is less than or equal to 8e over 3 factorial, which is 6. And if we think about the interval from minus 1/2 to 1/2, well, the biggest the absolute value of x can be on that interval is, well, at 1/2 or minus 1/2. So this becomes 1/2 cubed. And if you simplify this, it is simply e over 6. And this is approximately 0.454. So let's just see visually what this is telling us. So in the given plot, we have in black the function f of x equals e to the 2x, kind of this standard exponential curve. And then in red along with it, we have the second degree Taylor polynomial that we found centered at 0. And note, when we found the Taylor polynomial centered at 0, the Taylor polynomial and the function will always agree at that point, and then immediately around that point 0, we should get a pretty good approximation. So in our example, we are looking specifically from minus 1/2 up to 1/2. And what our remainder estimate, the 0.453, is telling us is the furthest those two curves will be away from each other is about 0.45. And we see, in fact, they're never that far away. It looks like they're pretty close here at their furthest. But that hopefully gives you a bit of visual intuition in terms of what our previous calculations have found.